In this video, we're going to talk about a new concept for us, and that's a concept of a heap, and also a little bit about priority queues, although that will be more in the next video, the next section. So we're just coming off of trees, so it makes sense that we go ahead and talk about heaps. So with a binary tree, you have two children. We know that, right? And we talked about the binary search trees, which are very structured. That every left child is bigger, and every right child is every left child is smaller, and every right child is bigger. Okay, so a heap is not a binary search tree. It's a different kind of a tree. It's ordered, but it's not fully ordered, or it's not ordered in the same way. Okay. So what a heap is, it's a complete binary tree. And by a complete binary tree, we mean that all the levels are full. Okay, level zero is full, level one is full, and level two is not full. So if it's not full, it's the case that any vacancies are to the right. Okay, so if 10 were missing, this would not be a complete binary tree. But we can have just one there or more than one, but they get added in this direction. Okay, so they get filled left to right. Okay, so heaps come in two basic varieties. It all comes down to what we call the heap condition. Okay. And the heap condition in a min heap, N is in minimum, is that each parent is smaller than its children. Okay. And a max heap where each parent is larger than its children. Okay. So this is not the same as a binary search tree because we're not relating at all to the siblings, basically. They don't have the same kind of ordering. Okay. So we do this because it's a little easier um, to deal with as far as making changes. There aren't quite as many um, conditions we have to meet. Okay. So the example I have here is of a minimum heap. Okay. So all the children of three are bigger than three. All the children of five are bigger than five. All the children of nine are bigger than nine, and so forth. Okay. So every parent is smaller than all of the children. That's going to be the heap property for us. Okay. So I think the good news coming off of the trauma of all the recursive algorithms we've been doing with binary search trees is that we're not going to use pointers to manage our heaps. Okay. Instead, we're going to use arrays. A lot of the examples that you may find online use vectors, and we're not talking about vectors till later. Vectors are part of the standard template library, which we're not dealing with yet. Okay, so we're just going to use arrays. Okay, so we're going to store the the heaps in an array in a special way. Okay, and we start at index zero with our root. Okay, so three is there. The next two positions are the next row, okay? And then finally, the last three are there. Okay, and again, there's possibility we could have one more here at index six, which would be our next value there. Okay, and that value would only have to be greater than nine. Okay, so we could put 11 there, and life is good. Okay, notice that 11 there would violate the binary search tree property, but not the heap property for a min heap. Okay. So once we construct our tree in this way, we have the ability through a formula to figure out how things work. Okay. So the left child of a node at any given position is 2i plus 1. Okay. So if I want to get the left node of the root, okay, it's going to be found at 2 times 0 plus 1, which is 1, and that's the left child of that. If I wanted the left child of 9, okay, which is at position 2, it's going to be 2 times 2 plus 1, or 5, and the left child of 9 is 12 at position 5. Okay. The right child, on the other hand, is at 2i plus 2, okay, because the left and right children tend to, or don't tend to, are definitely going to be next to each other. And then finally, if we want to find the parent okay, of a node, we take its position minus 1 and do an integer division on 2, which means we ignore any fractional portion that we get. Okay? So this is going to allow us to easily figure out where things go. Okay? So if we go through the process now, we want to insert a new element into our heap. Okay? So we have our array right here. Okay. In fact, we can write this in a more normal array form. Okay. Make this a little bit bigger. Okay. So we have our 3, we have our 5, we have our 9, 6, 10, and 12. Okay. And let's say that we want to insert 8 into this. Okay. We're going to start this process by inserting 8 at the end. Okay. So looking at our tree up here in a visual way, what we're saying here is we're putting this 8 right there. Okay. Is that better? No, that's better. Okay. So of course, this may or may not change it may not still be a heap, in other words. So this may not adhere to the heap property that we're looking for. Okay. So the way we're going to do that, okay, we're going to figure out if it's correct or not doing a process called percolating up. Okay. And we're going to start by comparing the 8 with its parent. Okay. And since 8 is in position 6, we can figure out the parent, okay, is going to be at position 2. Okay. We compare the 8 with the 9. Okay. And we want it to be that the parent is smaller, so that's not correct. Okay. So we have to swap them. Okay, so visually, we're going to swap here the 8. We're going to swap that with the 9. Okay. Um, so we have to make sure that this is not smaller than that, but it shouldn't be, at least in this case, it's not. So we can now stop and we're done. Okay, we check that versus that. We don't need to swap anymore. Okay. Again, this is all going to be through iterative as opposed to recursive because we're dealing with arrays. Okay. So we're then able to move that. Okay. If we wanted to add something else, no matter what it is, that's what we're going to do. Okay. We're going to just add it in wherever. We're then going to move it into the proper position. Okay. So the next thing we can talk about is deleting an element. So when we get to the next video in the next section on heap sort, we're going to be um, doing a max sort instead of a max heap instead of a min heap, which means the biggest element's on top. And a min heap, just so we're clear, the smallest element is on top. Okay, that's always the case. Now, if we added a 1, we would have to percolate that, and the 1 would go down here to the left of 6. Okay, that's our next position. The 1 would then get swapped to there, would then get swapped to there, and then get swapped to there. So 1 becomes the smallest value. Okay. So to do the heap sort, we're going to do the max heap, where the biggest element is on top always. Okay. And then to do the sort, we're going to remove that root. Okay. Because it's the biggest. So if we're going to take our tree that we have, we're going to start this process by moving the last element to the root position. Okay. So we start by taking the 9 and we're going to move it up here. Okay. We will have, captured 3 to print it out or whatever. Okay. 3 was in position 0 of our array. Okay. We now do a percolate down. Okay. So we have to make sure that we haven't violated our heap property. Okay. So in this case, we're going to compare 9 with its children. Okay. And the smallest of these is the 5. So we have to swap the 5 and the 9. Okay. And then we're going to compare 9 with its new children, 6 and 10. And 6 is smaller, so we're going to swap the 6 and the 9. Okay. And now we have deleted the root, but we have maintained the heap property. Okay. So that's the percolating down. Okay. So that's really all we're going to talk about for this one. So I put a tutorial out there, and for Monday's class, you should go through, I think it's the first 5 sections. Okay. It's up through the inserting and deleting from the heap. Okay. As a preview, what we're going to do next, we're going to use heaps first off to do a heap sort, like I said, because we're maintaining every time we add a new element. If it's a max heap, we know that the whole thing's not ordered. We don't have to do all the things we do in a binary search tree. Okay. But we know that the biggest element is going to be on top. So we can remove that. Okay. And then we can go from there. Okay. In order to sort from greatest to least. If you wanted to sort the other way, you could leave it in a min heap. Okay. The other thing that we're going to use heaps for is a priority queue. So a priority queue is a queue, but at every step we take the element that has the lowest priority. Sorry, the highest priority, which is the lowest number. Okay. So we're going to use a min heap to simulate a priority queue. Okay. So that's where we're going on this. So there's a homework assignment out there that we'll work on Monday. Okay. So this is a change of pace for us. We're still dealing with trees, binary trees in some ways, but I think the algorithms here are a little more straightforward because we're not having to deal with recursion. Recursion is hard and complex, as we have found. Okay, so make sure you take a look at the tutorial before class, and then on Monday we'll get started with this.